So, okay. Yeah.
Hello.
Hey, Richard. Hey. Okay, guys. 8th graders, we need to be quiet. Okay. Can I introduce you real quick?
Sure.
Okay. So, everybody, this is my cousin, also my godchild, Mr. Richard Reber. Okay. You know a lot about him already. Mrs. Poquetta spent a lot of time introducing him and showing you some of the things he's been working on, and even his really cool profile picture on Facebook, which we're all fans of. So because we know your time is very precious, I am going to kind of just scoot myself out of the way and let you talk, and when you're done doing that, they have about 5 gazillion billion questions for you.
Excellent. Well, I'm excited for it.
Okay, great.
They all went dark. Now I can't see anything.
Oh, okay.
So, this is what Nikki said. My name is Rich Reber. I am a systems engineer here at the Jet Propulsion Laboratory. That's in Pasadena, California, so just north of Los Angeles. And I am here today in our mission control room. We call this the dark room because, well, it's really dark, pretty much. But this is essentially the center of what's called the Deep Space Network. So JPL, we track and get data for all spacecraft that are outside of Earth orbit. So any spacecraft that leaves Earth, their data comes through this room. So the guy who runs this building calls this place the center of the universe. He's I don't think we're the center of the universe, but you get the idea. So we have 3 antenna complexes around the world. We have one in Goldstone, California, which is in the high desert here. We have another one in Madrid, Spain, and our third is in Canberra, Australia. Do you guys have those images? You get the images I sent you?
I did not.
No.
You didn't?
No. Did you send them through email?
Yeah.
I wonder if they went in our spam and I didn't see
Maybe
it.
they went to spam. If you have them on your computer, do you have that button that shows sharing screen?
Let me see. Ooh, I didn't share screen.
Okay.
Exciting. Okay, let me do that.
Yeah, me too. I thought, well, maybe because I could but.
Okay. You guys see that?
No.
No.
Well, we see you.
Okay.
No.
I'm not saying that
No, we see you.
Well, Mrs. Poquetta is checking her spam right now to see if we could bring it up here.
There it is.
Wait. Now it is.
Can't see your face. Okay.
That's all right.
What that means is they're all about 120 degrees apart. So it's supposed to be a meeting. So ignore that. So they're 120 degrees apart on the Earth. So what that means is we can always see every part of the solar system. So I think it's a really elegant choice of sites that they made, in that, like, if you look down on the Earth from the North Pole, which is this, the Goldstone, Madrid, and Canberra, they're all pointing in different directions. So as the Earth rotates, each antenna will be able to see a certain part of the solar system. So we have the ability to always talk to a given part of the solar system. So there's another really cool thing. Each complex has a bunch of antennas, and I want to show you this one. That is a 70-meter diameter antenna that's here in California, taken from like an airplane. But you can see there is a truck way down in here, just to give you an idea of scale. So that's 70 meters across, so that's roughly, what is that? A little over 3/4 of a football field across, and we can point that antenna to within millionths of degrees.
And the engineers are so good that built that antenna, they actually model how the antenna deforms as a function of the angle it makes. So as the antenna tips over, it starts to like potato chip a little bit and squish, and they know how that the shape of the antenna changes over time. I think that's super cool. They're amazing. But what's really cool about the darkroom here and what we do is, how do I stop screen sharing? Okay, so what's cool about what we do here is that we track every spacecraft that's outside of Earth orbit. We probably have a 99% usage rate, so only 1% of the time we have, only 1% of the time the antennas are not tracking spacecraft. And that's for like maintenance and the like. But we are still tracking a spacecraft called Voyager. Voyager has left the solar system. Well, there's two Voyagers. They have both left the solar system, and they're still going, and they launched before I was born in, I want to say 1977, they launched, and we're still tracking them. And they currently hold the Guinness Book of World Records for the longest running computer without a reset. They have not rebooted since they launched.
We
So,
reboot every day.
Sorry, was there a question there?
We reboot every day.
Yeah, they haven't rebooted their computer in 40 years. So we still get data from that spacecraft. And actually, when the spacecraft launched and the antennas were built, we would not have been able to track the spacecraft where they are now. And it's because we upgraded all of our antennas that we can now talk to them. I just think that's really sweet. Anyway, so I want to show you some other stuff. Okay. Oh wait, hold on. I'm gonna get the better picture. So Curiosity, which is currently driving around Mars, it's driven 14 kilometers, so that is like 9 miles in a few years. It uses its robotic arm as a selfie stick, and right around Christmas took this picture of itself at Bagnall Dunes, I think is the area. But if you go find this image online, it's incredibly detailed. I just want to zoom in on a bit. So that's the scale, the resolution that we have. So there's the antenna right here. This is the nuclear battery. It's called a radioisotope thermal generator. So it's a nuclear power source, so plutonium. And as the plutonium decays, it creates heat. And we take that heat and we convert it into electricity. And so that's how we power the rover.
We have a question.
Sorry?
We have a question about this.
Oh yeah, go for it.
Why does it take so long to get so very short distance?
Are you talking about our drive speed?
Yeah.
Oh, okay. That is a really good question. So I am actually working as the mobility systems engineer for the next Mars rover. So this is something I'm trying to improve for the next rover. The next rover we launch in July 2020. So we got some time to figure things out. But we don't really need to drive terribly fast. We do have to be able to drive very safely. So the wheels, let me show you some of the wheels. Okay, well, that's the wheel with the hole in it. So that's our middle wheel. So if we go slowly, we get much more torque. And so we can go up and over obstacles a lot better. So the wheels only rotate at a drive speed of 4.2 centimeters per second. Right? So that's like what, 2.5 inches per second. So we do a foot in like 15 seconds. Maybe my math is wrong there. Like 4 seconds. So we basically drive 152 meters per hour. It's very slow. And it's very slow because we don't really need to drive any faster. And if we drive faster, that means we have to be able to like detect hazards quicker and the like. So we just don't need to. And there's I'm sure your teachers are gonna hate me for saying this, but we have a saying in our line of work, which is better is the enemy of good enough. So we really don't need to be able to drive any faster, so we don't. If we drive faster, there's more. We're going to get more problems. But the way we drive is we don't really. Let me turn this off. We don't really. It's not like joysticking your remote control car. Right, the distance from Earth to Mars is so big that our commands travel at the speed of light. So the distance divided by the speed of light equals time, and that's how long it takes for our commands to get to Mars. And when Earth and Mars are at their closest, that distance is about 4 light minutes. So that means if I send a command, it will take 4 minutes for that command to get to the rover. Then the rover does something, and then it takes another 4 minutes for a reply to come back. And that's at the closest. At the furthest, when Earth and Mars are on the opposite sides of the sun, that time is something on the order of 22 minutes. So that means I have to wait between sending a command and getting a reply 44 minutes. So imagine playing like a video game with the worst possible lag you've ever had in your life. And you say, oh my God, there's an alien, bang, bang. And then it takes 40 minutes before you see what happened, right? It doesn't, yeah, so it's a long time. So what we do is we actually send a command, we send a bunch of commands in the morning, and the rover gets those commands, and then it executes them in order. So at a certain time, we'll tell the rover to, hey, break out your robotic arm and go drill a hole, or turn to the left and take some pictures. Or what we'll do is we'll take our imagery that we downlinked the day before, and we'll plan a drive, and we'll say, go forward 10 meters, turn to the left 45 degrees, and then go forward 5 meters. And that's how we drive. It's all like pre-planned, and then we send the commands, and then the next day we figure out what happened. So there's this one sol latency. So we call a sol, which is 1 Mars day, which is 24 hours and 38 minutes. So just over 1 Earth day. So we plan based on the Mars time, and so we tell the rover in the Martian morning to go do a bunch of activities. And then in the Martian evening, we get a downlink that has all the data. And then we get that data on the ground, and then we look at what the rover did compared to what we wanted it to do, and then react to that and plan our next drive. So that's how we drive the rover.
We have a question.
Yeah.
Okay, yeah. So you said that you can like drive it like manually with that, but can you like set the computer to do it like you don't ever need to like touch like a joystick or anything?
Yes, we can, and that's actually called AutoNav. So that's AutoNav driving. And so what we do is we'll give the rover a waypoint, and we'll say, hey rover, go to, we'll give it a coordinate, like, 150 meters forward and 50 meters to the right. Actually, we use Martian coordinates, but anyway. So we say, like, go over there, and the rover, once it, let me start over. So what we do is when we plan a drive, we will look in the direction we want to drive the day before, take some pictures, and we'll identify the hazards. We'll say there's a big boulder there, there's a big crater over there we don't want to go into, and then we'll plan a drive around those hazards. But after a certain distance, maybe 30 meters or so, our imagery is not high enough resolution for us to determine where hazards are. So we then turn on AutoNav, where the rover then takes its own imagery. It takes stereo pairs, so it's got a big, let me actually turn that, go back to that image so you can see what I'm talking about. Screen share. Yeah, so this here, this is the mast.
We can't see anything now.
Do you guys see that?
No.
We just see your name.
Oh, heavens. Something bad happened.
Now we see Cole. Thank you.
Are you still there?
Yeah?
Okay.
Did you lose your video feed?
Yeah, we did. Sometimes if you click on the video, oh, never mind.
Oh, we're back. I must have clicked something bad.
Yep, we're back.
Get that?
Yep.
Okay. So this here is what's called the RSM, the Remote Science Mast. And you can see there's two cameras here and two over here. And what we do is those are nav cams. We take stereo pairs, so a left-right pair, and then we make a blue-green or red-blue stereo image, and we wear like 3D glasses, just like at the movies. Everyone looks super cool. And we get those imageries in stereo. So the rover will do that. It'll take a stereo pair, and from that we'll create a 3D map of the terrain it's looking at. We'll find hazards, and it'll say, well, that's a big rock. I don't want to go, I don't want to drive over that rock, so I'm going to drive around it. So it plans its own paths. But the biggest problem we have, actually, is our computer is, I don't know how to say this lightly, our computer sucks. It's terrible. It's like 133 megahertz, the CPU clock speed. So like my Mac here is like 2.6 gigahertz. So roughly 20 times faster than the computer we have on the surface of Mars. And my phone is even better than the computer we have on Mars. And so we have very poor computational power on the surface, which makes it really hard to drive and do all the autonomous driving that we want. Now for the next rover, I get my very own computer just to do image processing. I'm so excited about this. Not everyone can say they have a computer on the surface of Mars, but that's, hopefully I'll be able to do that. So this computer is going to be dedicated just to do image processing. So we should be able to drive somewhere between 6 to 10 times faster than Curiosity. Curiosity spends most of its time actually thinking about where it wants to drive than it does driving. So we hope to turn that around and actually just like put the throttle to the max and say, hey rover, phone me when you get there. So that's something we're doing. So let me show you something else. I love this picture. This is one of my favorite pictures. This is.
We don't see it yet.
God, I'm sorry. Let me turn this on. Dude, even that's amazing these days. Hold on. This is an image taken from a spacecraft called Mars Reconnaissance Orbiter from a camera called HiRISE. And all these imagery is on the internet, they're public, but this is an area called Southwest Melis Chasma. Oh, dude, that's cool. I didn't see that before. So Southwest Melis Chasma is in a canyon called Valles Marineris on the surface of Mars. And Valles Marineris is the Grand Canyon of Mars. Only the Grand Canyon is puny compared to Valles Marineris. Valles Marineris, if you're going to drop it on the United States, would extend from Georgia all the way over to maybe New Mexico. And that's the size of this canyon. And Mars, being 1/3 the size of Earth, that canyon extends 1/3 around the circumference of Mars. That's the size of the canyon. So Malus Chasma is on the canyon wall halfway down. It's a big ledge. And by a ledge, I mean like 30 or 40 kilometers across. And this is some of the area of it. And there's a zoom in here. This is something that geologists put together. This is a really cool feature in Melis. This is a fossilized alluvial fan. So what that means is we believe there was a river that flowed out and created a river delta of sediment. And then that sediment got compacted and formed like almost something like sandstone. And then the material around it eroded away and it left this giant fan. So you get the idea. This is 500 meters. So this is probably, what, 3 or 4 kilometers? So that's maybe 2 miles across, 2 miles along here. I think this is absolutely amazing. This is one of our proposed landing sites for the next rover, Melis Chasma. Halfway down a canyon wall is a ledge with an old river delta. I think it's gonna be super sweet if we go here. And like, this is just north of that. These are, I don't even know what these are. I just think they're super cool. I'm an engineer, not a geologist, but anyway, this stuff is all online. I can give your teachers website links if you want. And there's some that are even higher resolution than this. And look at that. This is like geological layers, like you see on a mountainside. I think that's really wild. And this is all on the surface of Mars. And what's crazy is if you go around Earth and you look at stuff on Earth, you see very similar geological features. I don't know what that is, but that's really cool. That like fell away or something.
Yeah, that's what I was gonna say.
What's really cool is HiRise actually took an image of a Martian landslide in progress by chance. Anyway, so we looked at selfie. Yeah, that's all I got. I want to open the floor for questions for you guys.
All right. Okay. You want to go first? Yeah. All right, here we go.
So, Mrs. Paquette, I lost your video feed.
Okay, give me a second. Hold on.
Okay.
It's probably good for him.
Are we back?
Nope. Oh, something is doing a little spinny thing.
Okay, that's a good sign. Are we good? All right, we can ask the question. All right, go for it.
How long did it take you to learn all this stuff?
Well, probably started learning when I was born. I am always learning something new. Every day I try it. Well, every day I have to like figure something out, figure out how how to figure out where the rover is. So every day I'm learning something new. But I did undergrad in aerospace engineering, so that was 4 years. I did a 1-year master's in bioastronautics, which is like life support design. That was really interesting. And then I did another 1-year master's in space management at a school in France. So I probably went to school for 6 years after high school, but I am still learning every single day. As a systems engineer, this is what's hard. As a systems engineer, I'll go into a meeting, and my job is to figure out how different areas affect different other areas. So I've got, here's an example, is I have some really smart guys who are trying to improve our AutoNav algorithm. So how the rover figures out where the hazards are and to drive around those hazards. But the mechanical engineers that designed the wheels and the suspension have a limit over what size of obstacles we can drive over, and that affects the algorithms the developers are making. So there's this mechanical engineering and software path planning interface, and those guys don't speak that same language. So my job is to communicate between these people to make sure that everyone understands the constraints on the rover and the design and everything. So I go into a meeting with these people, and hands down, without any doubt, I am the dumbest person in that room. Right? So I'm in a room and guys have 1 or 2 PhDs, and I am just all right, why don't you draw that for me in crayons so I can understand what you're talking about? So that's basically my job. And so I'm learning every single day, and I love it. It's great.
Awesome. Next.
Yep.
So on the last photo you showed us, it was on Mars and all,
Yep.
but if it was on Mars, why wasn't it red?
They're black and white pictures.
Oh.
I am so smart.
So, has data volume, right? So, the more information you try and pack into something, the more data you have to transmit back. And each image that comes from high-rise, they're compressed, right? They're basically a really improved JPEG is what we transmit back from Mars Reconnaissance Orbiter. And for a given image, it's something like 200 megabytes, or something huge, absolutely astronomically large. So we can't actually, we don't want to send any more data than is absolutely necessary. So bandwidth is a huge issue. We don't have Ethernet to Mars. It's all over radio link that comes through the Deep Space Network. Yeah. Any more questions?
Yes, there's left.
Oh, lots.
Okay.
What year do you think you're going to be able to send a person to Mars?
Ooh, that is a good question. I think we'll have someone on the surface of Mars by 2035.
2035.
I'm guessing. There's a lot of technological challenges. The biggest I don't think we've solved that problem.
Okay. Next.
What is your favorite part of the job?
Let's see. I have really cool toys. We have a rover up in our Mars yard that we call Scarecrow. We call it Scarecrow because it doesn't have a brain. And what it is, it's a rover. It's the same mobility system as Curiosity, so it's about the size of a Mini Cooper, and but it doesn't have any of the guts of the rover. It doesn't have a computer. It doesn't have all the science instruments or the robotic arm, and so it's basically it's our ATV. And so what we do is we take that in the Mars yard and we just drive this thing around. Actually, it has its own Wi-Fi router, so you just connect to its wireless network, and then you can drive it from your phone, which I think is really cool. So we drive this rover the size of a Mini Cooper, using our phone, going up and down hills and up and over rocks, and it is so cool. But then, sure, we can go off-roading and joyriding, but there is a semblance of like intellect into this. There's so much knowledge that you need in order to understand what you need to do and how you're going to do it. And it's so fun. It's like really, really smart four-wheel driving. Well, six-wheel driving. But it's absolutely amazing. I love it. It's so fun.
Next.
So, with the SMAP, why did that take 800 tries to do?
I am not sure what you're talking about. Oh, snap! My quote from when I was the flight director. Wow. So the backstory here is SMAP has a big antenna that's 6 meters across. So that's what is that? 18 feet, 19 feet roughly. So it's a huge antenna. And that antenna opened once we were on orbit. So my job was to open that antenna on orbit. So I was the flight director for that activity. And this is an Earth orbiting radar. So it's still, it's still up in orbit, still working. We launched January of last year. So we've been operating for almost a year and a half now. So my job was to, first off, test all of the software that controls how the antenna deploys, and then figure out how we're going to do it for real in flight. So between all the tests I ran, I probably ran that deployment activity 800 times. Actually, I did a query of our test bed of all of the data, and I counted the number of times deployment started in our test bed, and it totaled up to 800 some odd times. So yeah, like all the different permutations, what happens if how does the spacecraft behave if this happens and that happens and that happens? What happens if we reboot in the middle of deployment? So running all those permutations, it's exhaustive testing, because this was one of the activities, if it doesn't work, everyone go home and dust off your resume because you need a new job. So it's one of those critical missions. Yeah, so 800 times, that was my lucky number.
Okay.
Thanks.
Great, good question.
Next.
So, how long, did you want to be something else when you were a kid, or have you always wanted to do the job that you have now?
Oh, that's a really good question. Did you guys just do a bottle rocket lab where you had water?
Yeah.
water?
Yeah.
Okay, so I did that when I was a junior in high school in my physics class. And for me, that one lab glued together math and science. And now I realize math was, useful, kind of easy, but I didn't really understand exactly how powerful it was until we did that lab in my physics class. And then I'm like, hey, so this is what math is used for. And that's when I said, hey, I am totally going to be an engineer. And I chose aerospace engineering really because I went to space camp when I was in 6th grade. So I went to space camp in Huntsville, Alabama when I was in 6th grade. And I looked at all the different programs that I could go into, and I chose aerospace. So that's how I got here. I haven't looked back. It's been great.
This is sort of goes back to what you said about Mars on the massive river delta. To your knowledge, do you believe that massive canyon was once a large ocean or a lake?
Oh, there was no question about that. Mars had a global ocean. It had rivers. It had lakes, it had ponds. Mars was very, very wet. The question is, how long ago was that? Or actually, let me see if I can find you this image. Recurring slope lineae. Hold on, I gotta, yeah, okay. This is gonna be super cool. Okay, screen share, go. Okay, you guys see that?
Yeah.
Yep.
Okay. This is called, this is something that the Martian geologists found all over Mars in like crater walls. And so if you actually look this up, there's like animated GIFs that show this. And what we're seeing is these lineae, this is called the recurring slope lineae. These form in the summer, and in the Martian summer, and then they disappear in Martian winter. Let me see if I can find one that's animated. Oh, this one's really cool. That was really small. Anyway, there's some that are absolutely amazing here. Yeah, and so what happens is these slopes, these lines, they appear in the summer and they disappear in the winter. And what that's actually traced it down to is that's liquid water. That is liquid water that's locked up, that's frozen in the winter, and it melts in the summer, and it comes out and it forms those lineae. But what's cool about the Martian surface is it's almost extremely salty. So that's not, the way to think about it is that's not salt water that's flowing. That's salt, that's wet salt that's flowing. Right, so if you take a salt shaker and you drop like a few drops of water into it, that's basically what's appearing there. So that's actually liquid water that we see flowing on the surface of Mars already. So, and then, what was it? Spirit, I think, one of the small rovers that landed in 2004, they found these little things called blueberries, which are, which they believe were minerals that were formed only during a very wet period. And then Curiosity found more evidence of liquid water at the mineralogical level. So yeah, we believe that we have extremely convincing evidence that Mars was once warm and wet. Yep.
Thank you. Riley?
Yeah, I do. So, like, saying that there was once water on Mars, like, do you believe there was once, like, a Martian civilization or aliens?
Intelligent life, probably not. Maybe microbial life, potentially. We don't have any evidence. We don't have any evidence supporting that or precluding that. So the jury's out. What we actually want to do with the next rover is we're sending what's called the sample caching system. So what we're going to do is we're going to take a bunch of geological samples. Like an earthworm, we take like dirt in the front of our rover, put it into test tubes, and then we like poop it out the back in these little test tubes. And we make these depots of test tubes. And so maybe in 10 years or so, we're going to send a fetch rover that's going to go pick up these samples and bring them back to Earth. So we're going to have a Martian sample return. And once we bring those samples back to Earth, we can do some extremely advanced studies of those samples, more than what we could do with any instruments on the rover. And so you can really look for life there. Yeah, more questions?
What's the hardest part of your job?
The hardest part of my job?
Yep.
I think the hardest part of my job is actually working with so many different people. Every specialist speaks a new language. Well, I don't mean like English or like Japanese, but I mean like different terminology. So I think the hardest part of my job is being able to work with so many different people and communicate what they're thinking and what they have told me. But I think communication between very smart people is the hardest part of my job. Yeah.
Good.
Any more questions?
What are your hours for work?
I usually work 8 to 5-ish. And I say ish, except for the last 3 weeks where it was 6 a.m. to 9 p.m. or 10 p.m.
9 p.m.
Yeah. We had a really long test that started at 6 a.m. and I had 800 pages of documentation to write. So I just finished that on Tuesday.
Ooh,
So like, yesterday I'm like, all right, I'm done. And slept for 12 hours.
I'm too tall. Do you ever stay overnight at that place?
I have, during a critical part of the development of SMAP, the Earth orbiting radar that I worked on, I was given this piece of hardware to test the software control of it. And that was a 36-hour test, but they only gave me 40 hours to run the testing. So I ran my tests continuously for 36 hours. And then, yeah, that was a rough day. That was a rough time.
What was your greatest accomplishment, do you think?
Probably Skype call with you guys. I think some of the most rewarding things I do is outreach activities like this. Last summer, I went to South Korea and taught space camp. And I'm actually going again this summer in August. And like teaching is, I think, the most rewarding accomplishment that you can do. Absolutely love it. Like getting you guys excited and interested in what I love is just amazing. So I love doing things like this, and I think these are the most rewarding things in my job.
Okay, you said there was water on Mars. Where did all that water go since it's not there? Well, it's there, but
Oh, cool question. That one is that's complicated. Okay. Have you guys studied like different material phases, like solid, liquid, gas?
Yes, we have.
Yeah? Okay. Did you look at a phase diagram? Temperature versus pressure?
We did, but I don't know. We did.
Okay.
We did.
Okay. So the atmosphere on Mars is only 1% as thick as Earth, so it's very low pressure. So frequently, you don't really get a liquid state of water. You get, what happens is you have frozen water and it sublimates into a gas. So that liquid phase is very hard to get. So you need a thick atmosphere, you need warm temperatures. So what we believe happened is, you know how Earth has a magnetic field, right? That's why your compass works. So in the core of the Earth is this molten core that's spinning, and that creates a dynamo effect that creates our magnetic field. And the magnetic field shields us from space radiation. So all this radiation in the solar wind is protected or is shielded from us by our magnetic field. So we believe that Mars once had a magnetic field that very similar to that of Earth, but that magnetic field has broken down. So what's happened is, since Mars is much smaller than the Earth, it has cooled, and that molten core is no longer, or the core is no longer molten, and it's not spinning. So you don't get that dynamo effect, so you don't get a magnetic field. With no magnetic field, you have the solar wind and the space radiation that hits the atmosphere of Mars, that excites the atmosphere and strips the atmosphere away from the surface. So we think, 1 billion years ago, Mars had a magnetic field that locked in the atmosphere, that shielded it from the solar wind and the radiation, that prevented the atmosphere from being stripped away. And as the planet cooled down, the core solidified and the magnetic field started to break down, and then all the atmosphere was stripped away by space radiation. That's what we believe. When the atmosphere was stripped away, more water started to sublimate, going into the atmosphere and then getting stripped away by space radiation. Well, what's interesting is there is a lot of frozen water on Mars. So if you look at the ice caps, the Martian ice caps come and go all the time as of the seasons. That's water ice and also frozen carbon dioxide, dry ice. So I think that's where the water went. It was stripped away by the solar wind once it became water vapor.
Wow.
That was a really good question.
That was. I liked that one. Okay.
Do you guys get paid overtime?
I work sometimes up to 90 hours a week, and no, I don't get overtime.
So, I have two questions. The first one is, are you one of the people that wanted to go to Mars when they were looking for people for that?
No, because the people that put out that call didn't know what they were doing, and they were going to kill everyone.
Okay, and then the second question is there like any proof probably on Mars like there was like living animals probably?
I'm sorry, was there any proof of
Like any life or anything, like animals or something?
We have been looking, by we I mean the scientific community, has been looking for evidence of life, and we have not found any yet. That doesn't mean there is not evidence. It just means either we haven't looked in the right spot, or we did not send the right instruments to find it. But actually one of the theories is we took a spectra, so we looked at all the wavelengths coming from Mars, and we found evidence of methane in the Martian atmosphere. And so methane can come from two sources. It can come from a geological source, but that's extremely rare, and the quantities we saw it in are quite high. The other source of methane is, well, biologic, like kind of cow farts, if you will. So we don't know. So we see methane on the surface or in the atmosphere of Mars. We don't know where it comes from. But one of the leading candidates is microbial waste creates methane. But we simply don't know. We don't know where it's coming from. So we're trying to figure that out.
Okay.
Good question.
So, yeah, me again. So, you guys study other things than Mars, right?
I have worked on three major missions. One mission went to a comet called Hartley 2. One mission is Earth orbiting radar that's measuring soil moisture content. And now I'm working on the next Mars rover. So we work on just about everything.
Okay. So this is kind of off topic from Mars then, but
Sure.
do you guys know where the center of the universe actually is?
Sure, right here. It says center of the universe. There's a. Let me see if you can see it. I don't know. That's not gonna work. Never mind. No,
Besides the building?
No. I have no idea. I don't think anyone has conclusively determined where that is. Yeah, that's a cosmological question that I am not educated enough to answer that one.
Okay, on average, how much money do you make?
Was that your bell?
No.
So starting salary fresh out of college for an aerospace engineer with a master's degree is somewhere between 75 to 80K, and it just goes up from there for annual salary. So that was when I graduated, which was like 9 years ago. It's probably gone up a bit, but that puts it into perspective.
Yep. Thank you.
What? Is my head shut? No, it's not. If you survey every... If you survey everything that orbits around the Earth, do you find any like unidentified things like UFOs? It doesn't mean spaceships. Like asteroids or whatnot.
So actually, the Air Force has a set of radar. I think they have one in Hawaii, one in Alaska, and they are continuously looking at all the things orbiting the Earth, and they actually create this like orbit map of all the stuff, and that can be like old rocket boosters, dead satellites. One of the astronauts on the space station dropped a toolbox, so they're tracking that. But unidentified stuff. I mean, a lot of it is unidentified, but it's tracked, and it probably came from some manned launch. So space debris is actually a big deal. The Air Force will send us an email if they believe our spacecraft is on a collision course with a piece of debris. And then that gives us like 2 days to maneuver out of the way of this debris. We call that a CARA, a collision avoidance. Anyway, I forgot what the acronym is, but anyway, we have to dodge out of the way of orbiting space debris. But I don't think any of it is extraterrestrial. The stuff that comes in from out of Earth orbit is going so fast, and it usually just hits our atmosphere and burns up. That's usually little dust and pebbles and the like. Yeah.
So have you ever lost anything due to space junk flying into it?
Me personally, I have not, but there's a company called Iridium which lost one of their satellites when a defunct Russian satellite smashed into it, and that was actually the first loss of a functioning in-orbit asset, and that was in 2009, I think. That was the first one. And actually, space debris is a big deal. Low Earth orbit is becoming a junkyard that we need to clean up, and it's just so hard to do. So that's going to be a big task that you guys are going to have to figure out once you're out of college. So good luck with that.
So why is there a vacuum in space?
Gravity. Gravity. All the gravity pulls in everything into the planet. So if there is gas in space, that gas gets sucked into the Earth and forms the Earth's atmosphere. So gravity just pulls everything in. So there's no material, there's no gas outside of space, because it's all the gas has been taken up by the planets and the sun. So, yep. Any more?
What was your biggest problem you faced?
Okay, this is a story. This is good. This is a good one. Unfortunately, I'm going to have to call it after this. I actually need to. But so let me tell you this quick story. I worked on a spacecraft called Impact. We were in the extended mission. So doing things the spacecraft was never designed to do on a shoestring budget. So we only had a flight team of 4. So there's 4 of us flying the spacecraft. And I am in charge of this activity. And we're loading new software onto the spacecraft. The first time we've done this in 8 years. So what we wanted to do was turn the spacecraft to a certain attitude, a certain angle, that would minimize the amount of fuel used for this activity. And so I send this command, we start this turn, and then all of a sudden the DSN, the antenna, they call up and they're like, hey, your signal strength is decreasing really quickly. And we look at our telemetry, the data, and all of a sudden we have this alarm on the spacecraft associated with the high gain antenna gimbal angle. So where our antenna is pointing is in alarm. So it like tipped all the way over and couldn't go any farther. And then I realized I had turned the spacecraft away from Earth such that the antenna couldn't point at Earth, with no way of actually bringing it back. And so the spacecraft was sitting off at this weird angle with no way to communicate. And that was my fault. Whoops. So we have a protection against that, and that's called command loss. So after a certain time, and unfortunately for us, it was 3 weeks. So 3 weeks later, the spacecraft is like, well, haven't gotten a command from Earth in this amount of time. I should start repairing myself to see if they can send me a command. And the first thing it does is point back at Earth. So it took us 3 weeks of sitting out there at this weird angle before the spacecraft gave up and said, all right, I'll point back at Earth. So that was my fault. I pointed the spacecraft such that we couldn't talk to it. Yeah.
Good story.
Could say that.
Good story.
Okay, well, thank you very much for your time. I know you have a busy day ahead of you yet. Thank you very much. Should we turn the lights on real quick so you can see all the kids clapping? Because I know we kind of turned it off so we could see you better. But, there, okay. And there are about 10 questions left, so if you don't mind, I'll instant message them and you can get back to me within the next week. And I'll be talking to you anyway to plan our California trip in August, and the girls already know you're babysitting when Jay and I rent the Harley, so thank you. All right, thank you.
Great fun.
Thanks. Bye-bye.
Bye.
That was fun. I can turn that into a DVD. 7th period.